Hey guys, welcome back to another RASK maths tutorial, and in this video I'm going to be proving this sum of squares formula. So this sum of squares formula is, in case you didn't know this notation, it's basically asking us to give a closed form expression for this sum. So it's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared, on and on, all the way up to n squared. Like so. So this is the sum we're basically working for, and it's defined for all positive integers n. So n is a natural number. And yeah, this is actually the result, in case you didn't know. But we're going to be getting to that. And there's just some things that we should know before we actually start this proof. And I haven't seen this proof anywhere else, so it's quite an original proof, quite cool. If you've seen a previous video on the fact that squares can be written as sums of odd numbers, we're going to be using that. But yeah, let me just show you guys what you need to know before we get into this proof. So first thing you need to know is that each square can actually be written as the sum of the first odd numbers. So what I mean by that is, you can see 1 is 1, 1 squared is 1, 2 squared is 1 plus 3, 3 squared is 1 plus 3 plus 5, 4 squared is 1 plus 3 plus 5 plus 7, and that pattern continues. So in a general term, you can write that n squared can be written as the sum from r equals 1 to n of 2r minus 1. Just like that. That's basically just the formal way of writing that. And yeah, the next thing you also need to know is the triangle numbers formula. So what I mean by that is the sum of numbers starting from 1 all the way up to n is of that number is just equal to n plus 1 over 2. This is just the triangle numbers formula. So this is 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. The way you prove this is using the fact that for any triangle number, you're going to have dots like this. So if n was equal to 3, the third triangle number has 6 dots, and that's true because 3 times 4 over 2, that is 6. The way you prove this is you basically create a copy of this triangle and put it on top of itself, like so. And then you observe that this has a height of n plus 1 and a width of n. So it has n plus 1 dots in total, but we got to divide it by 2 to account for the fact that we doubled it. So then we divide by 2, and that tells you what the nth triangle number is. So yeah, that's basically what we need to know. Those are the two things we need to know before we actually start this proof. So I'm just going to put these here and make sure you remember them. So now let's get started. First thing, I'm just going to write out the sort of expanded version. So 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. So let's just add an n minus 1 plus n squared. Now we're going to use the fact that we can write squares as sums of consecutive odd numbers. So we can rewrite this as 1 plus 1 plus 3 for the 2, plus 1 plus 3 plus 5 for the 3, plus 1 plus 3 plus 5 plus 7 for the 4. And this continues all the way up to these terms, which I'll just try and write out as quickly as possible. So we get all of this, plus we're going to get 2 n minus 1 for the second last odd term, plus, that's the final term. And then for this final n squared term, this can be rewritten as 1 plus 3 plus 5 plus 7, all the way up to plus 2 n minus 1 plus 2 n minus 1. Just like that. So now we've rewritten this sum of squares as simply the sum of consecutive odd numbers and then many rows of that. And now what we're going to do is we're actually going to sum these columns. So you can see this one column, well, this has n items. This 3 column has n minus 1 items. The 5 column has n minus 2 items. 7 column has n minus 3 items. This continues all the way up to the second last column, which has which just has 2 items. And finally, the final column has 1 item. So let's rewrite this sum again using this new information. So we can write this as n times 1 plus n minus 1 times 3 plus n minus 2 times 5 plus n minus 3 times 7, and that pattern continues, plus 2, or we can rewrite that as n minus n plus 2, right? Because these cancel out, and you can see how we can start to see a pattern, because let me just write this out. So n minus n plus 2 multiplied by 2n minus 1 minus 1, and then plus n minus n plus 1 multiplied by 2n minus 1. So we've got it in this form, and now what we're trying to do is we're trying to rewrite this into a different sum. So we're going to try and observe the general term, and hopefully you can see that these are simply just odd numbers. So we know what the general term for that is. It's just going to be 2r minus 1. And hopefully you can see that the n is actually just getting decreased by whatever r is. So, for example, here, actually, let's look at this one. Let's look at this one. This can be rewritten as n minus 0 times 1. Now, we know this can be rewritten as 2r minus 1. And if we use the counter r is going to be 1. But what we can rewrite this as is n minus r plus 1. So therefore, when r is 1, we're actually going to be subtracting 0. When r is 2, we're going to be subtracting n minus 1. And you can see that's going to increase linearly. So that should account for all these terms. And yeah, this here is therefore the general term, starting from r equals 1 and going up to r equals n, right? Because for this one, we just want r to be equal to n. So we can write this like so. And the term is going to be n minus r plus 1 multiplied by the rth odd number, so 2r minus 1, like so. And there we go. Let's try and plug in a value of r to see if this works. So let's just test it using r equals, let's try and get this term here. So r equals n minus 1, using a difficult one, but it should be fine. So the term we get is n minus n plus 1 multiplied by 2n minus 1 minus 1, which simplifies down to 2 times 2n minus 1 minus 1, which actually does work when you cancel those out. And you can see that corresponds to 2 times of this over here. So yeah, that's working. Let's rub out our test case. And now all that's left to do is let's expand and sort of separate out this sum. So expand this out pretty simply. We can just use okay, so we'll just use the FOIL method. This is going to be 2nr minus n minus 2r squared plus r plus 2r minus 1, like so. And now let's simplify and put everything in brackets of r. So r squared, that's going to be minus 2 plus r is going to be 2n plus 3. And then we have the constant term, which is just going to be minus n minus 1. Like that. Pretty simple. Okay. Yep, that looks good. Now what we can do is we can use separation of sums. So we can write this as, and while I'm doing that, I'm also going to use the fact that we can factor out sums, similar to how if you had r squared times, if you had this minus 2 at the front, and then you had minus 2 times 1 squared plus minus 2 times 2 squared plus minus 2 times 3 squared, you can just factor that out and then put that just like that, and then these two sums are equivalent. Using that, we can actually factor out these constant terms which don't rely on r to the outside of the sum. So doing all that, we get minus 2r squared plus 2n plus 3, sum of r equals 1 to n of r, minus n minus 1, sum of r equals 1 to n of just 1. Okay, and let's remember what we're actually trying to find here. We're trying to find the sum from r equals 1 to n of r squared, and you can see we have that in our answer. So I'm just going to rewrite in what the original thing was, and you should see that we have the same term on both sides. So I'm going to use an old trick of just moving this over, and this gives us 3 times the sum we're looking for, and that's simply equal to whatever these are. So now we can use the formula we know from earlier. The sum of the triangle numbers, the nth triangle number is given like this, and it's just going to be 2n plus 3 multiplied by the formula for this, which is n plus 1 over 2. So let's write that in over 2. And then let's subtract n minus 1 times the sum from r equals 1 to n of just 1. Well, this is the same as 1 plus 1 plus 1 plus 1 n times, also known as simply n, because this is just 1 times n. So that's just going to be n. Okay. Okay, so that's simply just going to be n. And now we're going to have to do some simplifying. So the first I'm going to do is I'm going to take a factor of n out. So, right, okay. So let's take a factor of n out here, and then this just becomes 2n plus 3, n plus 1 over 2, minus simply n plus 1, but I'm going to write this as 2n minus 1 over 2, so I can then simplify these fractions. Yep, that seems about right. And now I'm going to just put these all over denominator 2, simplify this fraction to get plus 3 plus 5n plus 3 minus 2n plus 2, which equals, let's collect a few like terms, 2n squared plus 3n plus 5 over 2. And if we want to factor this, let's just check how we do it. So right, okay. So I appear to have made an error somewhere. Let me just make sure there are no errors. Oh, okay, I found the error. Okay, here we go. See where this is a minus n and minus 1. So when I factor out the minus, that should actually be n plus 1. Yep, that makes sense. Okay, which means all of these should be pluses. And yeah, then I wouldn't have actually had to factor out this entire, I could have factored out this and this. It's all right. we can fix that. So therefore, that's going to be a -2, which gives a 1 there, +1. Okay, yeah, that makes more sense. So if we want to factor this expression, we can just do that. So that's equal to 2n plus 1 and n plus 1. So let's just write it like this, 2n plus 1 over 2. Okay, there we go. So we have 3 times the sum which we're looking for is equal to what we have on the right-hand side, which ultimately, if we divide everything by 3, we get the sum of squares is equal to n plus 1, 2n plus 1 over 6. There we go. And that's proved what we're trying to prove. So hopefully you guys like this proof. I don't think I've seen it anywhere else. And yeah, it's basically utilizing the fact that we can write squares as sums of odd numbers and then rearranging that sum to get it in a different form, which we can then rearrange and figure out, like so. So I think this was quite interesting. Thanks for watching, and I'll see you guys in a future tutorial. Bye.